Talking about you can't even notice.
Okay. Questions? One thing I did leave off on the exam topic list was potential of carbocation rearrangements. So, other than that, everything I think is on the chart.
Can we do an example problem with
The ring opening, an epoxide ring opening. Sure. So epoxide ring opening. And the other thing is I've been posting, people have been asking a lot of questions over the last couple of days and today, and you can ask during this if you want. If you don't want to ask in person, you can put it on Piazza because I've got that open. I've been putting a lot of answers on there, so if you're not like looking at Piazza, you might want to peruse it because there's some pretty good stuff on there, in my opinion. If I'm up till 10:30 last night writing out answers, that's, but that they're there. Sometimes if a question's asked again, I understand. I just relink something that's on there. So one of the questions that I just posted within the last half hour is epoxidation reactions as well as oxidative cleavage. What kinds of reactions? So the first thing is, how do we make an epoxide? And one of the ways to make the epoxide is to use the peroxy acid. So that's a peroxy. This is a peroxy acid. A peroxy acid is a C double bond O, OH with an extra O in there. What that will do is that will then make the epoxide out of the double bond. And so once we have the epoxide, then the question is, how do we open it up? And right now, the only way to open it up is to use what's called acid catalyzed, even though it isn't catalyzed, but use acid and a nucleophile to open this up. So for instance, if we use something like HBr, we take our epoxide and I'm going to react that oxygen with the H+. So in general, I mean, I say these things over and over again, some of these phrases, so that hopefully they kind of begin to stick. But if you were stuck on this reaction, oh, there's an oxygen and there's H+. So what's the first step? Protonate the oxygen. So we're going to protonate the oxygen, or you can think about what's the oxygen, electrophile or nucleophile. It's a nucleophile, so what can I react it with? The electrophile H+. So I'm going to go ahead and I'm going to protonate that. I'm going to protonate that oxygen. Okay, and so then I'm going to end up with a protonated epoxide. So this is always the first step to opening up an epoxide right now. Next semester, we'll do it with a base, but not now. It'll be with an acid. So that makes the oxonium ion. Now, the oxonium ion is not happy with a positive charge. So what's it going to do? It's going to take that positive charge and it's going to push it down into the carbons. So by pushing it down into the carbons, it's going to make something that looks like this. And then each of the carbons is going to share in some of that positive charge. And so then the question is, what does that look like? What kind of triangular intermediate? You have two choices. Bromonium ion or the mercury. So that epoxide, once you protonate it, it looks exactly like a mercury or a bromonium ion. Okay. And if you think about that, if you think about sort of the way things are laid out here, because, you know, somebody had to think about this, the reason that we're doing the acid catalyzed ring opening here is because this intermediate looks exactly like the bromonium and the mercury. That's why it's here, because it fits in with those other two. You know, I would say that's, you know, that's organizational genius on my part, but it really isn't. That's the way all books are written that way. And if they weren't, I would move it there. So then the question becomes, okay, where is the Br minus going to add? To what carbon is it going to add? The most substituted, meaning the carbon with the most substituted carbon is going to have the most. Yeah, that's what a substituted means, is it has the most alkyl groups. But in terms of charges, the most substituted carbon is going to have the most positive delta plus charge. It's going to have the most delta plus charge. And so the bromine is going to add to that carbon that has the most substituents, the most delta positive charge, and then the oxygen is going to swing over just like it would in a bromonium ion. If I went back and I wrote the bromonium ion and I said, we have a triangular bromonium ion, where's the water going to add? You would say to the most substituted carbon, because it has the most delta positive charge.
Wait, where's the arrow going? It's just breaking off at the oxygen carbon bond?
The oxygen carbon to the left bond is breaking and the OH is just swinging over. So in the end, what we're going to end up with is we're going to end up with the Br down here. There would be two methyl groups there. The OH would be over here. And then there's a hydrogen and another methyl group. So the nucleophile has to add from underneath, which means that the nucleophile I added and the OH have to be 100% trans. So if you're going to open up an epoxide, if you're going to do a ring opening, you have to use acid. And then the question is, well, what else could I use? I could use, in this reaction, I could use H plus Cl minus, I could use H plus H2O, or I could even use H plus alcohol. Any of those reagents I could use to open up the epoxide. And in the end, the epoxide would have an OH and a Cl. In this case, two OHs in that case, and an OH and an OR. So that's, I mean, if you wanted to write the mechanisms of any of these other reactions, it's the same first step to get you to this point, and then it's just a question of, okay, don't add Br, add water. And then form the oxonium ion, then lose your H plus like we've done in the past.
So those on the bottom replace the proxy acid to make
You have to use the peroxy acid in order to make the epoxide to begin with.
So the one at the bottom, which you would add.
They would go, so any of these reagents could go up here to replace the HBr.
So the proxy acid, what indicates you to know that this is
The peroxy acid is what we use to make the epoxide to begin with. It's one method to make the epoxide. Once we have the epoxide, then any of these reagents could be used to open it up. So it's just a question of, the question was, can you do ring opening? I decided to add in, remember that to make the epoxide, you need to use a peroxy acid, is one of the methods.
Alright.
Mary?
So, yeah, I was going to ask, like, if this is the first method, what would be the second?
The second method to make an epoxide is take that same double bond molecule, and first I'm going to add Br2 to it. Well, I'm going to add Br2 and water to it. Okay? So if I add Br2, bless you, and water, what am I adding to the double bond? A Br and an OH, Markovnikov, anti-Markovnikov. Markovnikov, what does that mean? That means the bromine's going to go where the hydrogen would normally go. And then the OH will go on the other carbon. And the Br and the OH add 100% trans. So just writing the product of this reaction, we would have CH3C, we would have an OH here, we would have the bromine down here, along with the H and the CH3 over here. So I added a Br and an OH, Markovnikov, which means that the Br, in this case, adding the Br and the OH, the Br is basically going to be the plus. That's going to be like the H plus. So on Markovnikov addition, we add the H plus to the carbon with the most hydrogens. In the bromination with water, we add the Br plus to the carbon with the most hydrogens. So this is the molecule we would initially make, the bromohydrin. Then if I treat the bromohydrin with a base, like hydroxide, what happens is it comes over and it deprotonates the OH. When it deprotonates the OH, I form an alkoxide. The problem now being, well, it's an advantage. The O minus now is going to act as a nucleophile, and since the Br and the OH, and now the O minus inheriting that position, is going to be in a perfect position to do backside attack, because the bromine and the OH added trans to begin with. So the O minus comes down, kicks off the bromine, and we can make that epoxide. So the second way to make an epoxide is to make the bromohydrin and treat it with hydroxide. That's method 2.
So if you're going to ask someone to make the exam, would you ask more like how you break the epoxide, or could you also ask how to form? Would you say
It would make sense to start with the alkene
okay?
and give you one or both of these sets of reagents to have you write the epoxide, and then open up the epoxide with whatever reagent that I wanted to. I could very easily do. I could do it a number of ways. We haven't necessarily focused on needing to know the reagents. Like, I could give you reactant and product, what reagent would you use? So that may or may not be, that probably isn't going to be part of this exam, but it'll be a big part of the future. Because our ultimate goal is to start to string reactions together to make more complicated molecules. In order to do that, you need to know the reagents that you would use to make each one of those molecules. But in this case, I could give you that, say what's the product, and I could even write epoxide, and then I could say react that with H plus Br minus and write the product, which is the reaction I just did earlier. So those are the two methods to make an epoxide. And if you look on Piazza, I actually did that in sort of a review sheet. I showed both of these again. Kaylee? It's a reagent that I'm using to make the epoxide. So it's not that it came from anywhere. It's like, okay, I just made my bromohydrin. Bromohydrins really, they're not good. They're not good. I dealt with bromohydrins a couple times in graduate school, and they are lacrimators. Let's see if we play password, or no, the pyramid game, right, which came back recently. Things that are lacrimators, onions, organic chemistry, things that make people cry, right? So lacrimators are like that. So they're not very useful compounds from the standpoint of they're hard to work with. Like I had to bag everything up and put it out in the hallway so there was no vapors, because I didn't want anybody walking. I didn't want the cleaning people walking in the lab because it hadn't all cleared out. Even if you do it in a hood, it doesn't all clear out. So they have only one real purpose, and that is react them with OH minus and you can make an epoxide. So I showed them in that context originally before Thanksgiving. So the OH is just another reagent that I added to it.
Can we do oxidative cleavage?
Sure. Okay. So those are two methods to make epoxides. That's how you open them up. Is everybody okay with that? So oxidative cleavage then is when you're going to cleave the double bond and convert them to carbonyls, either ketones, aldehydes, or carboxylic acids. So if you let's just take that molecule. So if I took this molecule and I wanted to do oxidative cleavage, I have 3 different reagents that I can use for this. The first reagent I could use would be KMNO4 and acid. Remember, KMNO4 and acid cleaves. KMNO4 and base is different. KMNO4 and base adds 2 OHs, 100% cis, but KMNO4 and acid cleaves. So I could do this reaction with KMNO4 and acid. I could do this with ozone and hydrogen peroxide, or I could do this same reaction with ozone and R2S. So I have 3 different reagents that I can use to cleave the double bond. And so in each one of these cases, the steps are going to be, first step is break or erase the double bond and put in 2 carbonyls. So in other words, for each one of these, I'm going to cleave them, and each of the carbons that was involved in the carbon-carbon double bond gets oxidized up to a carbonyl. Now, after I do the cleavage, I then have to think about the products that I made. In this case, I made a ketone. Once you make a ketone, there's nothing further that can happen to it. It's done. It's where it needs to be. But with the other molecule, if there's an H attached to a double bond, initially I'm going to make an aldehyde. And the question is the aldehyde oxidized by the cleavage reagents? And aldehydes will be oxidized if that reagent is KMNO4 or if it involves peroxide. So in this case, the KMNO4 will oxidize that aldehyde to a carboxylic acid. So the final products of this reaction will be ketone and carboxylic acid. Aldehydes are also oxidized to carboxylic acids by peroxide. So in the case of using ozone and peroxide, any aldehydes that were formed would be oxidized up to carboxylic acid as well. And the final answer would be ketone and carboxylic acid. R2S can't oxidize an aldehyde. So if it's R2S, you get a ketone and an aldehyde, and that's it. R2S doesn't do anything to the aldehydes. So once you cleave it, it's over.
But wasn't there a thing, I don't really remember, but it was like, if you have an aldehyde, that's not good, or?
No, there's two more cases.
Oh.
There's two more cases. So this is an acyclic double bond, and it's an acyclic double bond where the double bond is not at the end of the chain. I think you're thinking about what happens when the double bond's at the end of the chain. So we have a cyclic, what happens in the case of a cyclic double bond, what happens in the case of when the double bond is at the end of the chain. So let's do one at the end of the chain. So let's say I had this. So the end of that double bond is a CH2. If I treat this with, let's say, ozone and R2S, I'm going to cleave the double bond. I'm going to do exactly what I did before. I'm going to cleave the double bonds, and I'm going to turn them into a ketone. And then because the end of the chain is a CH2 group, it's going to become this aldehyde, which is the one carbon aldehyde, which is called formaldehyde. In the case of R2S, R2S doesn't oxidize the aldehyde, so at the end of the reaction, I'm going to have a ketone. Aldehyde, I don't need to do anything else. But if the double bond is at the end of the chain, and I now use either KMNO4, an acid, or ozone and H2O2, when I cleave the double bond, I'm going to do the same thing. I'm going to make a ketone plus now the aldehyde, but then what happens is the aldehyde in the presence of either the KMNO4 or the peroxide, now both of the sides of the carbonyl get oxidized so that I form that acid, which is H2CO3, which is carbonic acid. And in this case, carbonic acid is not stable. So what carbonic acid does is it breaks apart and forms carbon dioxide and water.
Your product would just be the ketone and then CO2 and H2O.
Yes, the final products would be the ketone and CO2 and water.
Would you want us to show that we took all the steps, or did you just
I'm looking for the final answer. But if you're looking for as many points as you can get, which is the point of the exam, is to get as many points as you can get. It's the way you want to approach it in sort of that positive way, as opposed to not lose points, because then you're going to be disappointed. If you're getting as many points as possible, you could still be disappointed, but it works better to work at it from that standpoint. Then if you were to show like the carbonic acid, you'd get all but maybe a couple points for the CO2 in water. So that might have been the one you were thinking about. There is something extra that happens when it's at the end of the chain. When it's at the end of the chain, you make CO2 in water because carbonic acid is unstable. Pop a can of soda. What's in there? Carbonic acid. How unstable is it? It's fizzing. Right. And when I talked about this, I did throw in sort of the idea that in the old days before spectroscopy that we'll learn about next semester in lab, before the days of spectroscopy, if you knew you had a double bond in your molecule and you wanted to know if the double bond was at the end of the molecule, and this is sometimes called a terminal alkene, if you knew, or if you wanted to know, what you did was you did this ozonolysis, or you did the KMNO4 acid, and if the reaction fizzed, then you knew the double bond was at the end of the chain. If it didn't, then you knew the double bond was internal. And so that could help you determine what the structure of the molecule was. And you determined you had a double bond in the molecule by taking red bromine, adding a drop to it, and if you did that and the bromine and the red color completely disappeared quickly, then that meant there was a double bond for it to react with. Could mean a triple bond though, but we haven't gotten to triple bonds. We'll start with that next semester. So that was a test, taking KMNO4 and base and getting the purple color to turn into a brown precipitate would also mean that you have a double bond in the molecule. Although that one's less specific because KMNO4 does lots of things. So that's the sort of the twist on this, is if it's the end of the chain, you get CO2 in water. If it's all one molecule, like this, and you were to react this now with KMNO4 and acid, you would again cleave it, only in this case because it's a cyclic molecule. Because it's a cyclic molecule, the molecule's going to stay intact, and there's just going to be one product. Then I would look at this, I see a ketone up here, no problem. I see an aldehyde down here with KMNO4. That means that aldehyde is going to be oxidized into the carboxylic acid, and so this would be the final product with a single molecule with a double bond, with a carbonyl, a ketone, and a carboxylic acid. And you can leave it like this. In both the handout I put on Piazza, as well as I think when we did this, I talked about numbering the carbons and basically straightening it out. You don't have to straighten it out. You may have to straighten it out if you're given multiple choice answers, but that's not Monday. So that's the types of ozonolysis and basically oxidative cleavage.
On the sheet that you sent out, it talked a little bit about SM1 and SM2 and like what might make something faster. Can you talk about that?
So, in what I'm thinking of in terms of those kinds of problems were if I gave you something like this, if I said, if I give you a pair of reactions and I say, which one of these two reactions is faster, or do they occur at the same rate? Okay. So you're going to need to, the only The only reactions I can give you to compare rates of are SN1 and SN2. E1 and E2 are not applicable. So if I gave you this kind of molecule or this pair and said, which one reacts faster, A or B? Or your other option is C, they react at the same rate. First thing I need to know is what mechanism is this? And they will always have the same mechanism. Comparing SN1 to SN2 is apples to hand grenades. Same shape, different action. You know how long it took in lab for us to do an SN2 reaction, right? We had to reflux it for 45 minutes. Had we have done that equivalent SN1 reaction, we would have put it in a centrifuge tube, capped it, done. Reaction would have been over. So there is this kind of misnomer that says, but wait, that was a one-step kind of SN2 reaction. It takes multiple steps in the SN1. That means nothing. SN1 will sometimes occur a lot faster than SN2. So you can't compare them, which means both these reactions have to have the same mechanism. And in this case, that mechanism is SN2. So that means you're going to have to remember your chart again as well. So both of these reactions go by SN2. The next step is what's different about these reactions. What's different is the nucleophile. So the third question to ask is, does the nucleophile strength affect the rate of an SN2 reaction? Yes, because the nucleophile shows up in the rate equation and in the rate determining step of the mechanism. But wait, this only had one step of the mechanism. Yeah, it's rate determining. So yes, the strength of the nucleophile does affect the rate of the reaction. So then the next question is, who's the best nucleophile? Who's the stronger nucleophile, hydroxide or fluoride? So then you have to go to the periodic table, and we have FONC. That's probably as far as we need to go. This is what kind of relationship? Horizontal. Who's a better nucleophile, OH minus or F minus? OH minus is a stronger nucleophile. Because when we're going horizontally, what are we basing nucleophilicity on? Base strength or basicity. And how does basicity increase? Going from right to left. And so hydroxide is a stronger base, therefore it's a stronger nucleophile. So this reaction would be faster. So then we could look at something like this. Which one of these two reactions is going to go faster? Again, the process, if I'm looking at these, what are these two mechanisms? They're going to be SN1. So both of these are going to go by SN1. What's different? The leaving group. Does the leaving group affect the rate of the reaction? What's the rate determining step of an SN1 reaction? Isn't that this? First step's rate determining step. Is the leaving group part of that? Yeah. Better leaving group? faster reaction. So leaving group does play a role. Better leaving group is going to create a faster reaction. So who's a better leaving group, chlorine or bromine? So now we have to think, what is the one thing that goes into leaving group ability? Exactly. So leaving group ability is based on one thing, basicity inversely. So what I'm looking for here is I'm looking for the best leaving group, which means of Br and Cl, which one is the weaker base? And it's Br. So bromine is the better leaving group. And so therefore that will be faster. Okay, so that'll be faster. B will be faster. Give you one more. Which one of these two reactions is going to go faster? Same rate. These are going to go by the same rate. I'm going to assume that one person is sitting there going, well, aren't you going to tell us why? I'll tell you why. Actually, I should ask somebody else why. Somebody who immediately blurted out an answer. Sabrina. Okay. It's SN1. We all agreed? Okay, next. So in that case, the nucleophile was not in the rate determining step. So the strength of the nucleophile doesn't matter. And what's different about these two reactions? The nucleophile. So the simple fact is, in this case, what's different is the nucleophile, but the nucleophile strength doesn't affect SN1. Therefore, they will go at the same rate. Okay.
On like one of the practice tests, there was one that the nucleophile used.
So then the other thing that might be involved in this is the solvent. So if I change this and I said, I'm going to react this one with water and I'm going to react this one with ethanol. Although let's come back to that in a minute. Let me modify the top reaction. Let's say I do the first reaction in water as the solvent, but let's say I do the second reaction in acetone. So it would have the same rate. So it's going to have the same rate with no solvent issues. But if I change the solvent, what does that mean? Well, we have to remember about the solvents. How do solvents affect the rates of SN1 and SN2? And I believe somebody asked about that as well. So, quick review. What is a Protic solvent? Protic solvents have OHs. Aprotic solvents don't. So aprotic solvents are things like acetone. Protic solvents are things like water and alcohol. It's the protic solvents that make the reaction go faster or slower. Because with the protic solvent, with the OH bond, the oxygen is slightly negative and the hydrogen is slightly positive. So protic solvents will solvate ions better than aprotic solvents. It all boils down to that. Protic solvents solvate ions better. So in an SN2 reaction, what are we doing? Our nucleophile is coming in and kicking off the leaving group. Do I want to solvate the nucleophile? Well, is it good to solvate the nucleophile really well? No. Solvating the nucleophile is going to slow down the reaction. Why? Because the nucleophile is trying to get itself in position to kick off the leaving group, to go into the transition state. And so the nucleophile, in order to get there, has got to drag all the solvent with it. Then when it gets there, it's got to get rid of the solvent in order to react. So having good solvation of the nucleophile will end up slowing down that reaction. So protic solvents will slow down an SN2, which means that the wasn't helpful there. So that the aprotic solvent makes an SN2 reaction go faster. So in an SN1 reaction, protic will slow it down by default. Aprotic will make it speed up. How about an SN1 mechanism? In this case, I'm breaking apart and I'm making the carbocation and the anion. Is solvation good here? Yes, because solvating the products does what? Makes them more stable. And if I make the products more stable, there's a whole Hammond's postulate that lowers the transition state and makes the reaction go faster. So in this case, the protic will make an SN1 reaction go faster. Again, aprotic's not really doing anything. It's all relative to the protic. So if the protic slows down the reaction, aprotic goes faster. If protic speeds up the reaction, aprotic is like go slower. So it's all because protics solvate the ions better. So we could make a chart. I think I made a chart in one of the previous answers that I've given on this. Is that if we said SN1, SN2, protic, and aprotic, and in SN1, protic is going to go faster, slower, slower, faster. But again, it's this column that's the most important because it's the Protic that actually takes an active role in either speeding it up or slowing it down. Does that make sense to everybody? And there's both written out things, and I think there's even, I've linked up videos in the past on Piazza. I have not, one thing I didn't anticipate was having to organize Piazza. It has all those little tabs at the top. They could probably be organized and all the answers shuffled into those different. I'm not going to do that right at the moment because then you're going to be like, where did that answer? I have no idea. Even after I get done organizing, who knows where it'll go. So I have both a video with what I've gone over here, because if somebody asked me this over the weekend, I'm going to say, see this video and then whatever time I started here as my example, Mary.
Is there an issue of like, so we've got Protic and aprotic, like, ready to slow down or speed up the reaction, but like that's not the only thing to consider. Like, what about if the nucleophile matters? Like, does one trump the other?
I'm going to try not to give you a problem like that, unless they happen to go in the same direction. But if you look at all the problems, ideally, they don't have more than one thing changed. Now, let's deal with this bottom problem. Well, we could deal with the top problem as well. So the top problem says, now we have water and hydroxide. This is still SN1. Does the nucleophile strength matter? No. What's different about this reaction? Well, the nucleophile and the solvent. Did the nucleophile matter? No. Does the solvent? Yes. So then we would look at this and say, okay, this is SN1, this is Protic, this is aprotic. Which one's going to make the reaction go faster? In SN1, it's going to be Protic. And so in this case, the top one reaction is going to go faster. Simply because it's SN1 and it's a Protic solvent. Now, the problem that you talked about on the older exams that shows up is, what if I say you're going to take a tertiary halide and react it with either water or alcohol? You might look at this and say, and there's two ways to look at this. You could look at this and say, well, those are nucleophiles, and therefore it doesn't matter. These two reactions are going to go at the same rate. But you could also look at this reaction considering that these are SN1 reactions, but also considering that these are examples of solvolysis reactions, because in solvolysis, the solvent is the nucleophile. So in this case, these are not only nucleophiles, they are also solvents. And so if you look at these from the standpoint of which one, they're both Protic solvents. So you might say, well, they still go at the same rate. All right, let's take the reasoning up a notch. Which one of these two is more polar? Because a more polar Protic solvent is going to solvate the ions better than the less polar Protic solvent. So of water and alcohol, which one is the more polar? Water. And so in this case, you could make an argument that this reaction is faster because it is in a more polar Protic solvent, and the reaction is SN1. I have in the past. The question is, how do I grade it? That's really the question, because if I grade it very narrowly, and that's what I'm looking for this one to be faster, which I have in the past. There has been one answer and it's been that one, then that's not as broad of a definition as maybe saying, okay, you're looking at it as a nucleophile and not as a solvent. So at this point, I probably wouldn't, because we didn't talk about this in the other class. But if you see that, I would give you in the end either answer. And I think in the past what's happened is when people have come in and protested about that question, we've gone over it and I've given them back the points. So that's what the faster reaction is. So that's where you're going to need to know about SN1, SN2. Okay. All right, if you have any questions, I will be in this weekend, at least in the afternoon. If the door's open upstairs, feel free. Otherwise, you can put your questions on Piazza. I'll be answering questions all weekend. Or you can just shoot them directly to me, and I'll answer them that way.
So,
Oh, and I have your sheets